Welcome to this video on empirical and molecular formulas of compounds. Today we're going to take a look at how to determine each of these, and I'm going to start off with just a little bit with the chemistry of candy. And so I think of candy as always having some sucrose in it, some sugar in it, and we actually see that even though each one of these candies has sugar in it, there's different amounts of sugar and different ways that they get put together, and that causes them to be uniquely different things. And so we see with compounds that the uniqueness of compounds is actually from not only the elements that compose the compounds, but how many of each one of those elements there are in the formula. And so we want to be able to determine those. So we're going to take a look at the difference between these. And so with empirical formulas, I'm going to move me up out of the way here. With empirical formulas, we actually know that these are the simplest whole number ratio, or the smallest whole number ratio of elements in their compound. And there's many compounds that can share the same empirical formula. I use EF for empirical formula here. And so many different things can share those. On the other hand, with molecular formulas, it's going to be the actual number of each element in a particular compound, so a unique compound, and so we see that this is unique for a given compound. And I think of this, there's one example that I like to always share. We can have something like CH2O, okay, and that's going to be the simplest whole number ratio, and then we could see over here where we could have like C2H4 O2, and that could be one type, and this is actually a type of sugar, and then we could have another type of sugar like C6H12O6, our fabulous glucose that we oftentimes talk about. Both of these have the same empirical formula, but they are very different molecules because they have different molecular formulas, and so those are both quite important for what we are actually looking at. So this is actually a series of steps that I use, move me down here now, in order to go through the problem solving. So you might want to pause this and write these down. I'm just going to point out a couple of things. A lot of times these are given to us in percent composition, and we need to change them into grams. So we just changed the percent into grams. You'll see me do that. And I'm going to go through these steps as I solve problems. And we see the empirical formulas up here, and then the molecular formulas down here. And you might be given them separately, or you might be given a problem that you're asked to do both, and we actually can do that. Okay. So the first one we're going to try here, back up over here, is what is the empirical formula of a compound containing 25.9% nitrogen and 74.1% oxygen. So we're going to go through and take a look at these. I'm going to grab my handy notes that I already have written out. Okay. And so we're going to start off with that 25.9%. We're going to make this into the percent, we're going to make into grams, okay, because we're going to assume a 100-gram sample. And we're going to make the 74.1 also into grams of oxygen. So I'm going to start off and I'm going to take my 25.9 grams of nitrogen, okay, and I'm going to, for nitrogen, convert that into moles. And so that was our first step. So for 1 mole of nitrogen, we have 14 grams on the periodic table. And when I calculate that out, I end up with 1.85 moles. Okay, so we end up with units of moles. Now with oxygen, I have 74.1 grams of oxygen because I changed that into grams from percent, and we have 16 grams for 1 mole, and so grams again are going to cancel, and we end up with a value of 4.63 moles. Now what we want to do is we actually want to do a mole comparison. So what I'm going to do is I'm going to divide both of these by the smallest number of moles. Now the least amount of moles is going to be the 1.85 moles. So I'm going to divide both of these by 1.85 moles. Okay. So when I divide by 1.85, I'm looking at a mole ratio. Okay. So I'm no longer going to have moles. They really cancel. And my ratio here, 1.85 divided by 1.85, gives me a ratio of 1. And down here, when I calculate this out, I actually get 2.5. Okay, 2.5 to 1. And in this case, we cannot have a 0.5. We never see a 0.5 or decimals in our formulas. And so what we have to do is we have to multiply both of these by some factor that's going to give us a whole number for both. So I'm going to multiply both of these by 2. Okay. And that gives me 2 here, and that gives me a 5 here. And our actual empirical formula for this is going to be N2 because we had 2 for N, and O5 because we had 5 for O. And so this is my empirical formula. Okay. Let's go ahead and try one that's a little bit different from that with calculating molecular formula. And so this is the simplest type of one that you'll see for molecular formula. And so this one says, what is the molecular formula of a compound with a molar mass of 60 grams per mole and an empirical formula of CH.N? So in order to do these, what I have to do is I have to figure out what the empirical formula mass is. So the empirical formula mass, okay, and so we have CH.N. So I'm going to add those together. So we have 12 for C, okay, plus 12 grams, plus 4 times 1 gram for hydrogen, plus nitrogen is 14 grams on the periodic table. And when I add those all together, I should get 30 grams, okay? 30 grams per mole for the empirical formula. Now what I do in order to find the what the actual formula for the molecular formula would be, I take the molar mass, okay, so I'm going to take the molar mass and I'm going to divide that by the empirical formula mass. So I'm going to take the 60 grams that I have up here per mole, and I'm going to divide that by my 30 grams per mole that I calculated for my empirical, and I end up getting a number of 2. Okay? And that factor is telling us that this mass is twice the amount of our empirical mass, which means our empirical formula, which means our formula has to be twice as much. So I take this number that I get, 2, and I'm going to multiply that times my CH.N to get my molecular formula, which should be C2H8N2. And so this here is going to be my molecular formula. All right, there are times where you might be asked to actually put all of that together, and that's what we're going to take a look at in the next example here. And I need to move me out of the way a little bit more. Okay, so we're going to try to do this for one that has an empirical and molecular formula for this. So we have percentages and we have a molar mass, and we need to have both of those in order to do this. So what I'm going to do is I'm going to start off, and I know that for carbon I have 38.7%. Remember, we can change our percents into grams, and so I'm going to have 38.7 grams. I'm going to convert my grams into moles. So for every 12 grams, we have 1 mole for 12 grams. Okay, and I'm going to do this for all 3 of them. So carbon, hydrogen, we have 9.7 grams, and I'm going to multiply that times 1 mole over the 1 gram. So 1 gram per mole for hydrogen. And then I'm also going to set up oxygen. So oxygen was 51.6 grams, and we have for every 1 mole of oxygen, there's 16 grams of oxygen. So we find those on the periodic table. So when I actually calculate these, I end up getting, in moles, I end up getting 3.225 here, and 9.7, of course, here, and then 3.537 here. Now, again, I'm going to divide by the fewest number of moles. This is the smallest number of moles. So I'm going to divide by 3.225, and I get 1 mole here. Okay, divide by 3.225, and I should get about 3 here. Okay. And then this last one, it's going to be really close to 1 mole. It actually comes out to 1.09. And what I will say is this. We're close enough here that we don't need to multiply anything. We can actually just call this 1 mole because it's within 1/100th or within a tenth, I guess I should say, of being there. So we can just call this 1. Okay, so these are in whole numbers. I don't have to multiply by anything. And so for our empirical formula, we know that we actually have CH3O. Okay, now I want to find out my mass of this. So the mass of this one, if I take my 12 grams for carbon and plus 3 times 1 gram for hydrogen plus 16 grams for oxygen, I end up getting a mass of 31 grams. Okay. But we know that the actual molar mass was 62. So I take 62 divided by 31, and that's going to give me a factor of 2. I multiply that by my empirical formula. Okay, so multiply that by my empirical formula of CH3O. And it turns out that my molecular formula is going to be C2H6O2. Okay? So I was able to determine my molecular formula and my empirical formula given all of this information. And so that's something you may be asked to do. All right. So that takes care of empirical and molecular formulas, but we actually have some interesting things that are called formulas of hydrates. And so what a hydrate is it's an ionic compound with a specific number of water molecules that are attached to it or bound to it. And we have the anhydrous form, which is just an ionic compound without any water. And so we have some names. We use those Greek prefixes that we've seen before. So we'll see Greek prefixes again to represent the number of water molecules. And we can use a dot between the ionic compound and the number of water molecules to represent how many of those water molecules we would have. So we see, this is an example, copper 2 sulfate, pentahydrate. If you remember from when we learned Greek numbers before, penta is 5. And so the formula for this is CuSO4. And then we see this little dot that's actually in between these two, and then 5H2O representing the pentahydrate. So we also can actually calculate these, and so let's try one example of that, and then we'll be ready to go and try this in the lab. So this one says, what is the formula of a copper sulfate hydrate that was 2.50 grams and changed when heated, resulting in 1.59 grams of anhydrous copper sulfate? Okay, and we're going to actually do this in the lab. And so this actually ends up being the pentahydrate, but we're going to see how we ended up getting that. And so in the lab, if we heat these things up, we'll see that there will be a mass change from the evaporation of water. And so the first thing I'm going to do is I'm going to actually calculate the amount of water that we had changed. So we want to know the amount of H2O that was evaporated. So if I take the hydrate mass and I subtract from it the anhydrous mass, so I'm going to take my 2.50 grams and I'm going to subtract from that the 1.59 grams. So that's the difference is what was evaporated. I end up getting 0.91 grams of H2O that was evaporated off. Okay. Now what I want to do is I want to convert my mass into moles, just like I did in the other formula stuff. And so for H2O, I know that my mass was 0.91 grams, and we remember that the molar mass for water, for every 1 mole of water, we actually have 18 grams. Okay, so I'm going to set that one up, and when I do, I end up getting a mass of water of 0.05056. Okay, Now for the anhydrous, which is just the CuSO4 without any water attached to it, we know that the mass of that was the 1.59. Okay, so 1.59 grams. And I want to actually convert that into moles as well. So for every 1 mole of copper sulfate, I've already done the math on this, it's 159.5 grams. And so when I calculate that one, I get 0.0099687. And I'm going to keep a lot of these numbers with me for right now. Okay, so now I'm going to divide by the smallest number of these two. Well, this 0.009 is smaller than the 0.05, so I'm going to divide by that number. Okay, for both of these. And when I do that, I end up getting 5 moles of water and 1 mole of the copper sulfate, copper 2 sulfate. And when you do these, you should always see the fewest number of moles is for your ionic compound, and then some number of moles, it could be 1 or more, of water. And so the way we wrote that, remember, was CuSO4, a dot, and then 5H2O. And that's actually our formula, and that's how we actually determine those formulas. We'll try this in the lab with a different hydrate. So I hope that was helpful for you, and we'll talk about these when we get back to class.